This lab was to collect data on a magnet falling through an aluminum tube in order to observe and apply Faraday's law. The fundamentals of the lab were Faraday's law, the Biot-Savart law, Newton's second and third laws, Ohm's law, the equation for the magnetic force on a loop, and the time derivative of magnetic flux of a dipole, the equations for all of which are shown to the right. The results of the experiment were that my experimental time was about 1.25 seconds, and the computational time from the model was 1.118 seconds. For the models and assumptions. For the models, the magnet was used to model a magnetic dipole, while the aluminum foil modeled a tube through which it fell. The assumptions, we assume that air resistance acting on the falling magnet is negligible, which feeds into the assumption we made that gravity and the magnetic force from the aluminum tube are the only two forces acting on the falling magnet. For the experiment itself, the system was the aluminum tube and the magnet, and the surroundings was everything else in the room. For the procedure, first using the magnetometer on my phone, I marked the north pole of the magnet. Then setting up my camera to record, I dropped the magnet through the aluminum tube 5 times. I then used the video footage to calculate how long the magnet took to fall through the tube for each trial, and took the average of each trial in order to come up with my final time. Here is my measurements and data. All of the important measurements for the tube and for the magnet are shown to the right, and then the times for each trial are shown in the table on the left, with the average being calculated at the bottom. For the checkpoint questions, why can't we use a ferrous tube, for example, a steel pipe? This is because the ferrous tube contains iron, and iron contains magnetic properties, so if a magnetic field from the iron had been induced, it would have interfered with the falling magnet, thus skewing our data. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet falls through the aluminum tube slower than it would in free space, as there is an upward magnetic force acting on it due to the induced current in the aluminum tube. For the computational model, we used GlowScript. As you can see, we first initialized all of our important physical constants, as well as the graph. Here we once more initialized more important numerical parameters and created the aluminum tube using the following lines of code, and we then created the bar magnet. After this, we defined the functions for both a magnetic field due to the dipole or the magnet, and we created a function for the magnetic flux created by the bar magnet. We then calculated the gravitational force on the magnet and the magnetic flux on a ring due to the falling magnet. Using this, we then calculated the current through the aluminum tube. The following lines of code were used to calculate the magnetic force of the falling magnet on the aluminum tube, and then the magnetic force of the aluminum tube on the magnet was calculated using Newton's third law. Finally, the net force was calculated by adding together the gravitational force and the magnetic force using superposition, and the changing velocity and position of the magnet were calculated using Newton's second law, and a graph was created in order to demonstrate this change in velocity as a function of time. Here's a picture of the computational model with the red ring representing the north pole of the magnet and the blue ring representing the south pole. The position of the magnet changed as it fell through the tube. Here are the graphs that were produced by the GlowScript model. As you can see, the graph on the right is the graph velocity as a function of time using my mu value from lab 3. This was not the graph that I expected, and the time was much lower for it to fall through the tube than it had been experimentally, and so after playing around with the mu value a little bit, I came to a mu value of 4.5, which created a much more accurate graph. For the questions relating to the GlowScript model, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? From above, the red current corresponds to counterclockwise and the blue current corresponds to clockwise, and I can know this using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Nothing much would happen. The magnet would still fall through more slowly than it would had there been no current, just the direction of the current would flip to what we see right now. How does the total time and tube of your real-world system compare to that of the computational model? How might the computational system be made more accurate? They were both relatively close when I used the second mu value of 4.5. It could be made more accurate by either splitting the tube into more rings or by reevaluating the magnetic dipole moment of the magnet and finding it again through experimental means in a more accurate manner. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The shape of the velocity versus time plot tells me that at the beginning, the forces being gravitational force and magnetic force on the magnet are unbalanced as the velocity either increases or decreases. Then they are balanced or equal to each other as the velocity does not change over the flat section in the middle of the graph, and then towards the end again as the velocity increases again, they are once again unbalanced with the gravitational force being greater than the magnetic force. For the discussion, there were likely no model discrepancies as a magnet can very accurately model a magnetic dipole. For potential source of error, considering air resistance likely was negligent over such a short distance of falling, the only source of error was likely human error when I was measuring the time that it took to fall through the tube, and possibly an incorrect value of mu due to error from lab 3. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If this were the case, due to Ohm's law, the induced current in the aluminum tube would be much greater, thus creating a much greater magnetic force on the magnet and possibly counteracting gravitational force altogether and preventing the magnet from falling. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If this were the case, the induced current in the tube would likely be less, as the now holes that are cut would disrupt the current, and the magnet would probably fall through the tube much quicker as a result of a lesser upwards magnetic force due to the lesser current. For the conclusion, this lab allowed us to gain a much more thorough understanding of Faraday's law and how it can be modeled in real life. This lab allowed us to more deeply understand induced current and EMF resulting from changing magnetic flux, and this lab gave us experience in simulating an important physics theory using everyday objects.